going to be turning our attention to the study of what are called sequences, and our first interpretation of sequences is going to be as functions. Suppose you have a set A, then a sequence in A is a function from I to A. So the domain I is called the indexing set, and the codomain A is what you have a sequence in. So this is the indexing set, and the codomain is what you are taking the sequence in. Typically, the indexing set is going to be the natural numbers or the integers or some subset of the natural numbers, like bigger than or equal to something, bigger than or equal to 1 being the most common. So here are our two most common indexing sets. These are the domain for our function, natural numbers 0, 1, 2, 3, or bigger than or equal to 1, 1, 2, 3. So it's really the same thing, just with 0 included in the naturals or not included in the positive integers. But all integers are also not an uncommon indexing set. Sequences carry over the notion of order from the domains. So if I have two elements of the indexing set, where m is less than or equal to n, we would say that f of m comes before f of n. It's not actually a claim as to which of these two things is bigger than the other. Okay, the set A, where these values live, might not actually have an order on it. It could be like letters or buildings, and you wouldn't have any sort of sense of which letter is bigger than the other or anything like that. So you're not making a claim about which of these two things is bigger than the other. However, if the inputs obey an inequality, you would say that one of these terms comes before the other. Okay, so we're just considering counting out values in the domain, our indexing set, typically naturals or positive integers. So we're counting out things like natural numbers, 0, 1, 2, 3, and we are correspondingly listing out values in the range. When considering this function as a sequence rather than a general function, okay, we just have some slightly different notation. So instead of writing out f of 1, f of 2, we use subscripts, f sub 1, f sub 2. But it's really the same idea. You are plugging in a specific element of the indexing set, for example, positive integers, 1, 2, 3, and you're getting out f of 1, f of 2, f of 3, and listing them. This is just a notational convenience. There's really no difference between writing out this and writing out this. Subscript notation for sequences is more common, but I wouldn't say it's universal. It's really not uncommon to see this sort of notation for sequences. So we can also write these curly braces, where we write f sub n in braces, where n is an element of the natural numbers. Here's our indexing set, and here is the function that spits out values of the sequence. You can also use this sub and superscript to indicate a starting index and a finishing index, but infinity represents going on forever. Okay, so this would be n goes 0, 1, 2, 3, and so forth. This would say n starts at 1 and does not stop, 1, 2, 3, and so on, and that's positive integers, or z+. The lower subscript, however, in this notation here, can be used to denote a different indexing set. Okay, we use plus or minus infinity if it doesn't actually stop, but you could do something like n equals 5 to infinity. So you would start with f sub 5, f sub 6, f sub 7, and so forth. You could have a negative infinity here and a positive infinity here, and then listing it out doesn't really have a start or a stop, but it includes f subscript and then any integer you want. So let's take a look at some explicitly defined sequences. These are sequences where the function is explicitly given to you. Okay, so we can exploit that in our notation. So for example, suppose our indexing set is integers, so we need to be able to plug in all integers, and our sequence is given by the following function. F of n is n squared minus 4n plus 1. Then we can write any of the following. Here we have f of n, where our indexing set is the integers, and also we are being told that the function is given as follows. But you could take this, that f of n is n squared minus 4n plus 1, and just stick it inside these braces to get this notation right here. The sequence is given by n squared minus 4n plus 1, where n ranges over all the integers. But you could also indicate that the indexing set is all integers by saying start in big air quotes at minus infinity and finish in big air quotes at plus infinity. In other words, include all integers in between these two values. So then we can write them out as lists of numbers. So here, if I change the indexing set to start at 1 and then never stop, this just says plug in 1 to get 1 squared minus 4 times 1 plus 1, which works out to be minus 2. Then plug in 2. And if I plug in 2, I get 4 minus 8 plus 1, which is equal to minus 3. Then plug in 3. 3 squared minus 4 times 3 plus 1, or 9 minus 12 plus 1, minus 2. Plug in 4, get out 1. Plug in 5, get out 6. Plug in 6, get out 13. So starting at n equals 1 and incrementing upwards, I compute these values and I list them out. If you didn't have the underlying function, however, just writing out terms of the sequence is really not the best idea. So if you were trying to define a sequence and all you did is say, oh, -2, -3, -2, and so forth, it would be really, really unclear if you weren't given any extra information exactly what the next term was supposed to be. It could have been this, -2, -3, -2, 1, 6, 13, or maybe it was a sequence that just went back and forth between those two numbers, -2, -3, -2, -3, and so forth. If all you're given is a couple values of a sequence, there's really no way to tell what comes next. So while it's sort of a common type of problem, oh, here are 4 terms of the sequence, correctly guess the next one, I think it's an awful problem, okay? And many people agree with me, and I will never give that sort of problem, because unless you are told what function produces terms of the sequence or what other method is being used to produce them, you really have no idea what comes next. And in fact, there shouldn't really be a notion of a correct answer. I might say, for example, consider the sequence 1, 2, 3, 4. What comes next? Did you say 5? Aha, you were wrong. I happened to be thinking of the sequence that goes 1, 2, 3, 4 and skips the number 5 and goes right to 6. If you didn't have any extra information, you'd really have no way of knowing. So those sort of guess the next term of the sequence are really pretty awful problems. So let's get more familiar with notation. In each of the following, we're going to have a sequence where a sub n is given by n squared plus n minus 1. So what's a sub 6? Well, all you have to do is plug in n equals 6 to get 6 squared plus 6 minus 1 for a final result of 41. So a sub 6 is 41. What about the following? A sub n, where n starts at 3 and ends at 7. This just says compute a sub 3, a sub 4, a sub 5, a sub 6, a sub 7, and then stop and list them out. So we compute A3, A4, A5, A6, A7, and we get 11, 19, 29, 41, and 55. So we have a list of 5 numbers. What is A sub k in general? All you have to do is take k and plug it in for n. K squared plus k minus 1. But with that in mind, we can do some more interesting things. For example, what is a sub n plus 3? Well, a sub n is n squared plus n minus 1. Then I'm adding 3 to it, and I can simplify this minus 1 plus 3 to just be a plus 2. So a sub n plus 3 is n squared plus n plus 2. But what about this? What is a sub n plus 3? It's not actually the same thing. Okay, a sub n was n squared plus n minus 1. A sub k, k squared plus k minus 1. Whatever the subscript is, square it, add it, subtract 1. So if the subscript is n plus 3, square it, n plus 3 squared, add it, n plus 3, subtract 1. Now if you expand all this out and collect like terms, you'll end up with n squared plus 7n plus 11. So that's what a sub n plus 3 is, and observe, it's probably not the same thing as a sub n plus 3. This plus 3 happened outside the term of the sequence. This plus 3 is within the index itself, and these are very different things. What about the following? A sub n squared minus a sub n squared. Well, a sub n squared says take the input and do this to it. Square it, add it, subtract 1. But the input here is n squared. So square it, add it, subtract 1. This other term, however, just says take a sub n, and once that's computed, square that. N squared plus n minus 1, all squared. So this gives you an n to the fourth. You have to expand all this out and collect like terms. And you'll end up right here, negative 2n cubed plus 2n squared plus 2n minus 2. So a sub n squared is different than a sub n squared. Now, if I didn't make such dramatic pauses with my voice, I could easily read this as a sub n squared minus a sub n squared, and it would sound like they should cancel off. Our verbal language for these things really falls short compared to our written notation. So always rely on things like parentheses to clarify. Was this squaring applying just to the index or to all of a sub n? So parentheses help. And this written notation is much clearer than just trying to speak it out loud. Explicitly defined sequences where you're actually given a function are one thing, but there's also a notion of what's called a recursively defined sequence. Okay, a recursively defined sequence is one where earlier terms of the sequence are used to compute later terms. So a sequence could be given as follows. A sub 0, if the index is 0, you are explicitly told that a sub 0 is 3. In general, if you know the value of a sub n and you add 2 to it, you can get the value of a sub n plus 1. So what are the values of a sub n as n goes from 0 to 4? Let's figure this out. We need to compute them, a0, a1, a2, a3, a4. We know the value of a sub 0 is 3 because it was just given up here. But for the others, we're going to rely on this recursive formula. So a sub n plus 1 is equal to a sub n plus 2. If I plug in n equals 0 into this expression, we get a sub 1 is a sub 0 plus 2. We already know a sub 0 is 3, and 3 plus 2 is 5. Therefore, a sub 1 is actually equal to 5. This recursive formula says the next term of the sequence is given by the previous term plus 2. So if I knew this was 3, the next one will be 5. Well, what comes next? If I let n equal 0, we get a sub 2. Here's a sub 1 plus 1, a sub 2 is a sub 1 plus 2, but we've already computed a sub 1 is equal to 5, and 5 plus 2 is 7. So a sub 2 is equal to 7. If you continue in this manner, you'll get a sub 3 is a sub 2 plus 2, 9. A sub 4 is a sub 3 plus 2, 11. Okay, let's take a look at another example. Depending on whether the domain, aka the indexing set of a sequence, what kind of set that is, recursive formulas can also be used to go backwards. In the previous example, we used one term to get the next one, but you can also use a given term to get the previous one. So with the same formula, if we used all integers as an indexing set, you could plug in n equals minus 1. So instead of the index starting at 0 and then counting forward, we need to account for negative indices as well. Okay, so let n equal minus 1. And you'll get a sub 0 is a sub negative 1 plus 2. Well, now this is the value we know, a sub 0. 3 is equal to a sub negative 1 plus 2, and you can solve this for a sub negative 1 and get 1. In fact, you can then rearrange the recursive formula. Instead of a sub n plus 1 is a sub n plus 2, if I just subtract the 2 over to the other side, you'll get this right here. So now you can more easily compute. If I know this term, you can compute the one before it. So for example, a sub negative 2 is a sub negative 1 minus 2. That's just letting n equal negative 2 and using this formula here. A sub negative 2 is a sub negative 1 minus 2. Well, we already computed a sub negative 1 to equal 1, and 1 minus 2 is negative 1, so there we are. A sub negative 3 must be a negative 2 minus 2. We computed a negative 2 to be negative 1. That's what this work here was. Negative 1 minus 2, that's negative 3, etc., etc. Recursive formulas can actually involve the index itself. You could, for example, have a sub 0 be given to be 3, but a sub n plus 1 is a sub n plus 2n minus 1. Notice that the index n isn't just showing up in the index, but it's also showing up as part of the recursive formula. So now, given a sub 0 equals 3, a sub 1 must equal a sub 0 plus 2 times 0 minus 1. That's just letting n equal 0. If I let n equal 0, we get a sub 1. a sub 0, 2 times 0. A sub 1 is a sub 0 plus 2 times 0 minus 1. A sub 0 was given to be 3. 3 minus 1 is 2. Letting n equal 1 gives me a sub 2 equals a sub 1 plus 2 times 1 minus 1. A sub 2 equals a sub 1 plus 2 times 1 minus 1. We already computed that a sub 1 is 2. So putting a 2 here, I get 2 plus 2 minus 1, aka 3. If I let n equal 2, a sub 3 equals a sub 2 plus 2 times 2 minus 1. A sub 3 equals a sub 2 plus 2 times 2 minus 1. We've computed that a sub 2 equals 3. 3 plus 2 times 2 minus 1 overall gives me a 6. And then continuing forth, we would get, for example, a sub 4 equals 11. The index is a perfectly legitimate thing to show up in the expression for the recursive formula. Okay, in the explicitly defined sequences, of course we had the index show up, but this throws a lot of people off. In recursive formulas, you can use earlier terms of the sequence, but you can also use the indexing variable itself. Okay. That's recursion that only depended on the previous term of the sequence. But a recursive formula could depend on more than one term from earlier in the sequence. So for example, if you know a sub n and you also know a sub n plus 1, maybe this formula gives you a sub n plus 2. To productively use this formula, you would need to know 2 terms of the sequence, and then you can get the next one. So for this formula, we need to know 2 consecutive terms of the sequence, and then I can get the next one. So suppose a sub 0 is 2 and a sub 1 is 1, and we have this formula. How would you compute a sub 4? Well, first you'd have to build up and compute a sub 2. So let n equals 0 to get a sub 2 equals 2a sub 1 minus a sub 0 minus 3. There it is. We know a sub 1 is 1, and we know a sub 0 is 2. Computing all of this out gives you negative 3. So a sub 2 must equal negative 3. But now that I know a sub 1 and I also know a sub 2, I can compute a sub 3. The same formula tells me if n is equal to 1, I get a sub 3 equals 2a sub 2 minus a sub 1 minus 3. We've already computed that a sub 2 is negative 3, and we were given that a sub 1 is 1. Computing all of this out gives me that a sub 3 is negative 10. Now that I know a sub 2 and I also know a sub 3, this formula will help me compute a sub 4, which was the goal of this exercise. Letting n equal 2, I get a sub 4 equals 2a sub 3 minus a sub 2 minus 3. A sub 4 equals 2a sub 3 minus a sub 2 minus 3. We've computed a sub 3 to be equal to 10, a sub 2 to be negative 3, and here's just a flat constant of minus 3. Working all of this out gives me negative 20. So overall, a sub 4 was negative 20. Now this was an example where 2 consecutive terms were used to define the next one. There's really no limit on this. I can have a recursive formula that needs 38 consecutive terms of a sequence to get the next one. As an example of a recursive sequence that is so special it's given its own notation, factorials. So the factorial numbers are defined as follows. Okay, they're going to be given their own notation in a bit, but for now, since we want to lean on sequence notation, we're going to write them as follows. A sub 0 is defined to be 1. To get the next term of the sequence, take the next index, note that this n plus 1 is the same as this, times the previous term of the sequence. So let's compute some of them. A sub 1 is 1, so this here must be the same as that. So a sub 1 is 1 times the previous a sub 0. We were given that a sub 0 is 1, 1 times 1 is 1. And at this point you might think nothing very interesting is going to happen. But a sub 2 is 2 times a sub 1. Okay, this 2 is the same as that one. We've computed a sub 1 to be 1, 2 times 1 is 2. A sub 3 is 3 times the previous term, 3 times 2 is 6. A sub 4 is 4 times the previous term, and 4 times 6 is 24. A sub 5 is 5 times the previous term, and 5 times 24 is 120. A sub 6 is 6 times the previous term, and 6 times 120 is 720. These numbers are getting really big, and they're going to continue to get extremely large. Now, if you tried to run this recursion backwards, okay, we have established that sometimes recursive formulas can be run backwards. Well, if you tried to do it backwards, okay, you'd have a problem. You'd get a sub 0 is 0 times a sub negative 1. Okay, a sub 0, this index is the same as this multiplier, and the previous index goes here. So a sub 0 is 0 times a sub minus 1, but this is not possible, because a sub 0 was given to be 1, and 0 times anything is 0, so there's no solution. You actually cannot run this recursion backwards. So starting at a sub 0 equals 1, this can only be run forwards. Now, instead of calling these a sub n, this sequence gets its own special notation, n factorial, with this exclamation point. And they're used for counting how many ways to arrange things, and oh boy, are we going to be using them later on in the course. Okay, so what we've computed here, 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, and so forth. So the notation is 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, 6 factorial is 720, and all we're doing, instead of using a sub n, a sub 4, we're calling that 4 factorial. Okay, so the factorials are just the terms of this sequence. 1, 1, 2, 6, 4, 120, 720. The next one you would multiply by 7 and get something big, I don't know. Okay, so these get bigger and bigger. There are other special sequences that get their own discussion, and a very famous one is the Fibonacci sequence. So this is a recursively defined sequence. It's called the Fibonacci sequence, and it's given by the following recursion. F sub 0 is 0, F sub 1 is 1, and it's a two-step recursion. I need two terms of the sequence, and I add them together to get the next one. So if I know two consecutive terms, if I add them together, that will equal the next term. So let's compute a bunch of them. F sub 0 is 0 is given. F sub 1 was 1 is given. But now F sub 2 must be the sum of the previous two terms. That's just taking the recursive formula and plugging in n equals 0. F sub 2 equals F sub 1 plus F sub 0. Two consecutive indices added together gives me the next index term. F0 plus F1 gives me F2, also a 1. But then F2 plus F1 will give me F3. 1 plus 1, okay, we computed F2 as 1, and F sub 1 was given as 1. 1 plus 1 is 2. Now that I know index 3 and index 2, I can add them together to get index 4. F sub 3 was 2. F sub 4 is overall 3. And it looks like we're just counting 1, 2, 3. But notice we didn't start off that way. 0, 1, 1. So we actually duplicated a 1, and now we're just counting, but if we keep going, F sub 4 was 3 and F sub 3 was 2. Add them together to get 5. So 0, 1, 1, 2, 3, 5. The next one will be 3 plus 5 is 8. Then 5 plus 8 is 13, and so forth and so forth. So this recursive formula actually represents a lot of natural phenomena. It can be used to model growth of colonies of organisms like bacteria. So suppose, for example, a bacteria takes a single unit of time to mature, and every mature bacteria can spawn a young bacteria. So we have mature bacteria and young ones. Young ones can become mature, and mature ones can split off new young bacteria. So if you begin with one young bacteria as time progresses, you'll have one young bacteria. So at 1 unit of time, you have 1 young bacteria. Then it becomes mature, so you have 1 total bacteria. But now, the mature has spawned a young one. Overall, you have 2 bacteria. The mature one is now going to spawn a new young bacteria, but this young bacteria is going to grow old. So you have 2 mature and 1 young. To be clear, the 1 young bacteria you have now is not the same one you had before. This young bacteria became mature. The mature one spawned another young one. Those 2 mature bacteria spawn 2 young bacteria. This young bacteria becomes mature, so I have 3 total mature ones. These 3 mature bacteria spawn 3 young ones. These 2 young ones become mature, combined with the 3 I already have to have 4. So this sequence is actually telling me how many bacteria total I have, and so forth. This Fibonacci sequence, perhaps it'd be nice to have an explicit formula rather than a recursive one. In the prior example, f sub n was telling me how many bacteria I have after a certain amount of time, and maybe someone asks, well, what about after 100 steps? And you don't want to go through the work of computing via the recursive formula, f sub 5, 6, 7, 8, 9, all the way to 100. It'd be really nice to have an explicit formula that you could just plug in 100 to and compute the result. Okay, so is it possible to compute a later term of the sequence without relying on the recursive formula, without relying on all the previous terms? Yes, it is. Not always, okay, but for the Fibonacci numbers, yes. In fact, the following formula is known as Binet's formula. The nth Fibonacci number is given by, this is the Greek letter phi, and this is the Greek letter psi. Phi to the n minus psi to the n divided by the square root of 5, where phi is the number 1 plus root 5 over 2, and psi is the number 1 minus root 5 over 2. So this is a complicated looking formula, and it is kind of unpleasant to compute things out by hand this way, but it is, at the end of the day, an explicit formula that you plug n into, and it tells you which Fibonacci number you can get out. So, for example, f sub 2 can be computed by phi squared minus psi squared all over root 5. Here's phi squared minus psi squared over root 5. Now, computing all of this mess out actually comes down to as follows here. 6 plus 2 root 5 over 2 minus 6 minus 2 root 5 over 2. Various things cancel, and what you are left with is 2 root 5 over root 5, which simplifies down to 2, which is correct, thankfully. Why does this formula work, however? Can we prove that it works rather than just have it be given to us? Well, the answer in this case is yes, we can prove it, and in fact we will, but we're not going to do it right now. Okay, we're going to close with a discussion of what are called Collatz sequences. So here's an example of a recursively defined sequence. Suppose you start with an arbitrary positive integer. So a sub 0 is just n. Pick whatever you want, 12, 28, 324. Okay, whatever you pick will define a different sequence, but it starts with something and you can pick whatever you want. To find the next term, however, we do this case-wise analysis. If the previous term was even, divide it by 2 and that gives you the next term. If the previous term was odd, multiply it by 3 and add 1, and that gives you the next term. The resulting sequence is called a Collatz sequence, beginning with, well, whatever you picked as your first term. So suppose we start with a sub 0 equals 2, so we're letting capital N be 2. Well, since that term is even, we compute the next one by dividing by 2 and adding, and then we end up with 1. Since that term is odd, we compute the next term by multiplying by 3 and adding 1 for a result of 4. Since that is even, we compute the next term by dividing by 2, and that result is 2. But now we're back to 2, and we actually know that if a term of the sequence is 2, the next term should be 1, and then 4, and then 2. So in fact, we have this cycle. 2 is followed by 1, is followed by 4, is followed by 2, is followed by 1, is followed by 4, and so forth. So the sequence is just going to repeat this over and over again. Every time you're even, divide by 2. Every time you're odd, multiply by 3 and add 1. So 2 is even, divide by 2. 1 is odd, times 3 plus 1. 4 is even, divide by 2. 2 is even, divide by 2. 1 is odd, times 3 plus 1, and so forth. But what if we started with a different number like 7? Well, 7 is odd, so start by doing times 3 plus 1 to get 22. 22 is even, so divide by 2. 11 is odd, so times 3 plus 1. 34 is even, so divide by 2. 17 is odd, so times 3 plus 1. 52 is even, so divide by 2. 26 is even, so divide by 2. 13 is odd, so times 3 plus 1. 40 is even, so divide by 2. 20 is even, so divide by 2. 10 is even, so divide by 2. 5 is odd, so times 3 plus 1. 16 is even, divide by 2. 8 is even, divide by 2. 4 is even, divide by 2. 2 is, oh hey, we're back in this case where 2 is followed by 1 by 4. 2, 1, 4. Does that always happen? No matter what I started with, would I eventually hit this pattern of 1, 4, 2, 1, 4, 2, 1, 4, 2 forever? Nobody knows. Okay, a lot of work has been done on this, and there are some results, okay, that we're not going to get into, but overall the question is, if you start with any positive integer, will you eventually hit the pattern 1, 4, 2, 1, 4, 2, 1, 4, 2? And there isn't a known answer to this, okay? If you start with a number up to something really enormous, computers have worked it out, and every number that's ever been tested has eventually reached the pattern 1, 4, 2, 1, 4, 2, and so forth. But we don't know if it always happens. If we could find a single number that we could conclusively say never reaches the pattern 1, 4, 2, 1, 4, 2, problem done. Does it always happen? No, I found a specific example where it doesn't. But just using a computer to check some starting numbers, and in those cases always getting this pattern, doesn't tell me if it always happens. And nobody actually knows the answer to this question as of the recording of this video. As I mentioned, people are working on this, and you never know, someone might announce a solution.